Welcome, everybody. It is 2 o'clock. We'll get started. Thank you all so much to join us today. And this is our first webinar in this series in the spring semester. And we will have one every month until April. So thank you again for coming. And today I'm really excited to have Professor Patrick Underhill joining us talk about connections that inspire.
Thanks a lot, Lucy. Thank you for organizing this really unique series and letting me sort of talk to you about my research. I put on the title slide this picture of a space shuttle in orbit. And like many people of my generation growing up in the 1980s and 90s, I was really fascinated and inspired by space. And I was actually lucky enough to go to space camp, and that really expanded my interest in space. I was also really interested in outdoor activities, and getting out and hiking. My mother actually also had a store where she sold cooking supplies and gave cooking lessons. And so I really liked cooking growing up. And those have continued into today. I recently was able to go to Kennedy Space Center and complete the Lego Saturn V rockets, hiking over this river using a bridge made of 3 cables, or cooking, like making fresh pasta and ice cream. And those were the types of things that I was really liked growing up. And you might wonder, because I'm not an astronaut, I'm not a park ranger, I'm not a chef, right? What does this have to do with my research? And that's kind of the point, is that there are these connections that hopefully I'll share with you in the next few minutes that have really inspired us as we've been doing our research. I began college at Washington University in St. Louis, and I started in chemical engineering. But I was also really fascinated as a freshman in my physics classes, including a special relativity class I took. And I was sort of torn between sort of the chemical engineering and physics, and viewed them very differently. I ended up getting degrees in both of them, but felt somewhat torn because that was not the most common combination. But some of that really changed when I did some undergraduate research at Michigan State University at the cyclotron there, where they're shooting nuclei at some target and then watching what flies off. And we were doing computer simulations of that, of these collisions and what comes off from those collisions. But instead of using sort of nuclear fission reactions to figure out what comes off, we were actually treating these like a hot drop of nuclei and how it would cool off by evaporating drops of other nuclei. And so those were the same kinds of things I was learning in chemical engineering in other applications. And so I saw those connections across disciplines. But also this relates to these ideas in everyday life. For example, when I was sweating, hiking the fiery furnace hike at Arches National Park, or watching the steam come off of the hot springs at Yellowstone National Park, or even just cooling down my hot tea. And so that was able to not just inspire us, but actually use those tools in order to understand a very complicated problem. And that continued into my PhD work at MIT, working with Pat Doyle, where we were examining DNA in microfluidic small channels and trying to manipulate those molecules to have better separations and diagnostic tools. And to do that, we had to take these DNA molecules, which were all coiled up, and stretch them out where they wanted to pull back. And so we were drawing analogies and connections between things like this DNA and everyday objects like a rubber band elasticity pulling back, or when you're making, say, bread dough and it pulls back due to that elasticity. And we were actually able to use those connections and ideas of elasticity from these other examples and figure out how to accurately apply them to these DNA molecules in these small channels and come up with better models to be able to design better diagnostic devices. And then that continued in my postdoc work at University of Wisconsin-Madison, working with Mike Graham, where we were trying to understand these concentrated suspensions of bacteria that are swimming around and how they might coordinate their behavior to work as a group separately than they would as individuals. And if you've been sort of watching the sky and seeing birds, you might notice that a similar thing might happen, say, with these starling birds that are able to move around as a group and coordinate their behavior. And the more you look at this, you see this all around. Actually, some other researchers noticed this with humans as well. They put cameras at mosh pits and watched the people moving around in the mosh pits, and they would sometimes spontaneously form these circle pits where it would start rotating around. I haven't experienced that in a mosh pit, but I was hiking along by some tide pools and found these organisms on the top of the water surface as they were sort of coordinating their behavior. And so the idea was we were trying to use these ideas and inspiration from these different scales in everyday life to understand these swimming organisms and how as they swim, they have to push the fluid out of the way and cause a flow that affects the other ones. And in some ways, they could sort of draft off one another, but how do you put that into the correct details at the scale of bacteria? These fluid flows can be different depending on the different sizes and materials that they're made out of. And we can also observe that in everyday life. For example, as I was hiking and found this fountain, you can see the really nice, smooth, laminar flow coming out of that fountain. But then we can have very different types of flows of different materials, either a very rough, kind of turbulent flow, or the flow of the air over these sand dunes we were hiking on that left these ridges in the sand. And so what we were able to do is use some of those ideas to understand how these bacteria would coordinate their behavior by using computer simulations, either on the left where we are tracking and simulating every single organism by these two beads, the red and the cyan beads, or by tracking the concentration field of how many bacteria are in different regions. And what we found was that even just these passive fluid flows they create could actually cause this coordinated behavior, even if they don't want to do that. And that might have implications for how these organisms work together as groups to mix chemicals or move around faster. I then started as a faculty member at RPI, and my goal was to have a research lab that draws across these connections from disciplines, from science and engineering, from sizes, from atoms up to microscopic, up to planetary scale, and applications from industrial to everyday uses. A natural first starting point was combining my two past research experiences of these swimming organisms coordinating their behavior, but now doing it in a complicated fluid. And we are inspired by things in the body, like saliva and mucus in your body that acts as barriers to infection. They also have these elastic properties. And that might seem very not everyday life. It's more like things like this book and movie Fantastic Voyage, where people had to shrink down and navigate through the complicated kind of barriers in a body to save a person's life. But what we found when we did these simulations was on the left is one of these simulations in a simpler fluid like water. But when we did these simulations in a fluid like the saliva in your mouth, we found that that saliva would inhibit the ability of these organisms to move around and coordinate their behavior. And what was important in changing this response from the coordinated behavior to the interrupted behavior was a number called the Deborah number. It was a different value for these different situations. And although this may seem somewhat foreign to you, that concept of the Deborah number is actually all around us. So the story goes that the Deborah number was named after a story in the Bible in which Deborah said that the mountains flowed before the Lord. And the idea then behind this number is that depending on how long you're observing something, if you're observing something for a really long time, it can have a chance to actually flow, Whereas if you're absorbing it for a short amount of time, it isn't going to flow and act more like a solid. So for example, when I was hiking in the Swiss Alps here, I didn't notice the actual mountains moving. Or as I was looking at these sort of Canadian glaciers, I didn't see them moving. But we do know that over long enough time scales, those actually do move. And how this connects to these saliva and bacterial systems is that as the organisms are trying to coordinate their behavior over that time frame, can those polymers in your saliva, can they relax or not? And it turns out that they can't, and so they act more like a solid that can interrupt that behavior between the organisms. We're now using these types of models to understand other systems, like the flow of mixtures of polymers and particles and proteins, and applying simulations where we have objects that interact and want to stick to one another and come out of solution. For example, one of these simulations that we're doing tracking the concentration of these things falling out of solution and thinking about how can we apply that to things like water treatment or phase separation or precipitation for purifying drugs. And we see that all the time in everyday life as well. As I'm making a cheese, as I'm causing those proteins to come around and stick with one another. Or a lot of food products where the interactions of these things change their arrangement and the properties they have, like in ketchup or mayonnaise. And I use this a lot in my classes as well. I have a tradition of bringing in of the last day of class something that I've made, for example, like these cheesecakes with jelly and whipped cream and chocolate, or these Oreo sort of macarons with buttercream frosting. And that's all around us that can really inspire us. For example, we're using kind of foams like you would see on the beach and using that to understand assembly in polymeric particles. But you may have noticed I haven't actually mentioned my interest in space up until now. But last year, I was actually lucky enough to work with Amir Hirsa here and be able to go and see my first launch down in Florida. And we were sending samples up to International Space Station. And we were looking at relatively large drops of proteins that we would make these nearly spherical drops. And then we would turn one of the rings that would cause a flow. And we could use this unique environment of going up into space to make these really big drops. And we could then use that to understand things on Earth and how proteins will interact and flow, for example, in the human body, but also to understand things like mixing and microgravity in terms of thinking about trying to manufacture new materials in space. And then recently, we're also using the quantum computer we have here on campus. In particular, we're using this to try to accelerate assembly calculations like the ones that I showed here. And this way, we're also connecting back to over 20 years ago when I was taking quantum mechanics classes for fun and using that today in this language to understand these kind of material processing situations, but also relating to everyday life, like making cheese. So I hope I've shared with you some interesting examples where we can use things like glaciers to help us understand how bacteria move through our saliva, or your hot tea cooling down to understand collisions of nuclei, or these sort of foams on the beach and understanding polymer assembly, or even how can we connect sort of cheese making with quantum computing. So I've also had a lot of interesting connections with people that inspired me. And I just wanted to highlight a few of the faculty that were important in the specific projects that I was talking about here, and the funding agencies that funded these specific projects. But before we open it up to questions you might have for me, I just wanted to challenge you with a question, which is to think about how can you use these types of connections of size or material or application as inspiration for your own work. So thank you very much for listening. I'd be happy to try to answer any questions you might have.